Hi, everyone. Thank you so much for choosing to see this talk. Well, my name is Amy Merrill, and I'm with American Rivers, and the name of the talk is, Does Hydrologic Restoration of Mountain Meadows Result in a Net Increase in Carbon Storage? This is the 5 or 6 year project, and I am here to tell you about what we've found. Okay, well, meadows are beautiful. There are about 18,000 meadows in the Sierra Nevada. They cover around 275,000 acres. That's only about 2% of the region's area, but they hold 12 to 30% of the soil carbon in the region. So they're small but mighty. Also, meadows are lovely. They're hotspots of biodiversity. And they're home to over 1,400 native vascular plants, including 170 special status plant species, with 38 times more native plants in meadows than in their surrounding uplands. Healthy meadows provide habitat for birds, amphibians, bats, all kinds of wildlife, not to mention our favorite plant species. And they are important natural reservoirs of water, clean, cool water, and they hold it like sponges and release it later on in the summer when everybody needs it most. Sadly, over 60% of our meadows are degraded. Incision in the channels over 100 or more years of, ill-advised management has dropped the groundwater table out from a lot of meadows, meaning that the plants can no longer access the water. And so you can have transition into sagebrush flats when it used to be a very rich meadow full of different kinds of sedges and forbs and all kinds of grasses and things. This can be recovered if you restore the bottom of the channel, elevate it, and thereby elevate the groundwater level through restoration. There's a lot of work doing that right now, and goals of having 30,000 acres of meadows restored by 2030. And we're nearly halfway there, so welcome you to join us with the Sierra Meadows Partnership. Many things change with meadow restoration. First of all, yes, you can increase the bottom of the elevation of the bottom of the channel. You increase channel sinuosity. You provide water so that you have a much greater productivity in your vegetation. You can also increase, our hypothesis, the storage of carbon in the shallow and in the deeper reservoirs of the soil. So that's our main hypothesis, is that this is what's going to happen. Because when you look at healthy meadows now, they're the biggest carbon reservoir. The biggest carbon reservoir is in the soil, and they are very rich, dense areas of soil carbon. So it had to get there somehow, and we think it was when they were healthy. So our overarching question then is, does hydrologic restoration of meadows result in a net increase in soil carbon storage? And if so, how much, for how long? And what are measurable covariates? How can we know that a meadow is going to increase its storage of carbon before we restore it? Or what can we do to really make sure that that happens, in a holistic way? But how do you measure carbon that's going underground? It's hard to see. It's underground. And so we had to figure out how to do that. And the way that we decided to approach this, and my partners in this, by the way, are Ben Sullivan of the University of Nevada at Reno, and Steve Hart at UC Merced, among many other people have worked on this, but those two were the advisors on this. They're both biogeochemists, so helpful. Anyway, conservation of mass approach is the idea, where we measure as many things as we can and solve for what we can't measure. And what we can't measure is what's going on in the below ground carbon inputs, but we can measure above ground carbon inputs coming from litter. We can measure the changes in the reservoirs of the soil carbon, year 1 to year 4. What's the difference? We can measure change in reservoir of the roots, change in the litter. And we can also measure what is going out of the meadow. The flux of carbon dioxide and methane coming off the soil can be measured, and same with leaching losses of dissolved carbon that goes out through the groundwater. And then we can solve for the unknown, which is that little faucet there, what's going on to the below ground. 15 meadows from the Kern River Plateau all the way up to the Feather River. We have 7 impact meadows that are being restored. Each one is paired with a control. 2 of the restoration ones had 1 control that remained degraded over the project period. And then we have 2 reference meadows that were in what we thought was excellent shape. So those are the meadows that we looked at. We measured carbon inputs, senescent biomass, litter in the fall, carbon outputs, those are the greenhouse gases coming off the soil, leaching losses, which we actually estimated, and then changes in storage of the reservoirs, of the soil carbon and the root reservoir in years 1 and 1 year before restoration, and then several years after restoration. We measured those things and looked at the change over time. And then the hypothesized covariates are things that we thought would change with a big increase in carbon storage: wetland species cover, percent vegetation cover overall. Precipitation obviously is important, and then depth to groundwater. So water and plants, those are the main things. Sampling design, we have a 24-point grid. Each grid point is 30 meters apart. The Sullivan lab with Cody Reed measured the independence of those points at the beginning of this project and found that they are independent. And at each one of those grid points every month in the year prior to restoration and then the year after restoration, we measured greenhouse gas fluxes and soil moisture and temperature. And then in the midsummer, we measured the vegetation, species composition, and percent cover in square meter plots at each one of these grid points. Litter carbon was measured in the fall, and then again we measured the changes in the reservoirs of root carbon and soil carbon down to 75 centimeters. How do we measure gas flux? Botanists don't always do that, but we do have one botanist that helped us. Rob Toms was out there helping a lot of dates measuring our gas fluxes from the meadows. So basically we take a chamber top and you put it on the ground and snug it, make it snug. And then you have a syringe with a needle in it and you withdraw a little bit of gas at say 1 minute and 10 minutes and 20 minutes. And then you measure the concentration of those gases and the change in gas over time to give you a flux of the rate at which the gas is coming off the ground. So that's how we measure the gases. Okay, so here's a couple of meadows that are included in this study. In the Kern River Plateau, Bonita, one of the reference meadows, and then Osa, you can see there's a lot of bare ground there. This is pre-restoration. Then going down to the foothills, at Bean Meadow in the Merced, drainage, highly incised channel, and Middle Martis up in the Tahoe area, a lot of incision there. And then Loney Meadow in the Yuba River drainage was overseen by Circle. And then Upper Loney was a reference site, and Deer Meadow was the degraded control. Okay, so those are our meadows and our methods and what we're doing. And the findings are that what did restoration do what we expect? Well, yes, it did significantly increase the groundwater level in the growing season. It did. There was a significant difference between the restored and the control for the surface soil moisture in the growing season, and an increase in the cover of the wetland plant species. With the groundwater elevation, they all had an increase in the groundwater elevation compared to the controls, except Truckee Meadow. And so Truckee Meadow did not. And because of that, we threw it out of the rest of the analysis. Sorry, Truckee had to go. And one of the big questions that I think I didn't mention was when you have a wetland, are you going to increase the amount of methane that is emitted from the wetland? Wetlands are the biggest natural sources of methane in the atmosphere. And methane, as you all know, we're all composting now, right, is a very strong global warming greenhouse gas. And it has about 72 to 80 times the power for global warming as a molecule of CO2 in the first 20 years. And so we need to pay attention to it, and increasing the water available in a meadow would logically increase the amount of methane that's released. And in fact, it did in 3 of the meadows significantly, and oddly, those were the 3 meadows that are shown here. And some of the fluxes are not that large, but for some of them, the fluxes are somewhat large. But if you compare it, as I will in a minute, to the total amount of gas that's absorbed through productivity, it becomes less than 5% of the overall budget. So an increase, but not a big increase. How about nitrous oxide? Nitrous oxide, 300 times the power of a carbon dioxide molecule, but released it in very small amounts, and some of it is actually consumed. Did restoration elevate the total below ground carbon? Well, here's the funny thing. It didn't in all of them. It only did in 3 of the 6. 2 of the 6 actually showed losses of below ground carbon compared to their control sites. It might be that this was too soon after restoration and they're still kind of in the recovery room. Maybe 5 years from now, they will show a big increase in their carbon storage compared to their controls. But 3 years later, not so much for those 2. But 3 of them did show big, actually, it's a very big number for an amount of carbon that's been allocated below ground. So a mixed answer there. And are there indicators that a meadow will increase its below ground storage? Can you figure out where you're going to be on this graph before you actually go about your restoration? Or is there something that you can do to ensure that you'll actually have a little bit more carbon stored below ground after the restoration? Well, what we found is that yes, plants do matter. In fact, it was the frequency of graminoid species, grasses, Elaeocorus, sedges, juncus, that have a strong correlation to the increase in below ground carbon that you get with restoration. So this is cool. It's got an R squared of basically 0.9, very significant, within a pretty tight range of sedge frequency. So I think we're just going to assume that this line doesn't continue off into enormous amounts of carbon storage, and probably just say if you have 45% or more frequency of graminoid species in your grid, then you have a 1,500, say, grams per square meter per year of carbon that can be stored in that site. And again, this only goes to year 3, so this doesn't go on into the future forever. We need to have more information on that. The best way to measure changes in soil carbon, we found you don't have to take all of the measurements with the roots and the gases and a lot of the other things. The main thing that you need to really do is get good measurements of the carbon that is in the soil down to, here we have down to 75 centimeters, gives you a R squared of the actual soil carbon that we measured of 0.95. So not easy to get those good measurements, but if you get those, then you're basically good to go. Okay, the change in soil carbon overall below ground is shown here for all of the meadows. The red bars represent the total below ground carbon allocation for each meadow. This is by family or each group in each cluster. And then these multicolored bars show the different components of the calculation for the below ground carbon storage. And these numbers are exceedingly high, almost 5,000 grams per meter squared per year for this year. If we compare this to other meadows, other systems, these blue bars are our study. They're like really tall compared to the rest. These are global numbers from all different kinds of systems. So it's a little nutty. But meadows can be nutty. And what we think is happening is that we took these measurements in the middle of a big bad drought and then after the drought. And it's really likely that these numbers that we saw are really a short-term response to 2017 when there was a lot of water. Okay, I'm wrapping up here. Meadows are rich carbon reservoirs. They're dynamic. They seem to change annually. We can't just take a measurement in 1 year and know that that's it. The plants matter. We need to know more about the relationship between the plants and the changing weather patterns, climate change, and how that affects the carbon storage. A lot of people helped with this, a lot of institutions, and we're very grateful. Right, thank you. Look forward to talking to you.